Okay, we're going to do chapter 1, section 7 on inequalities. So an inequality is very similar to an equality when we come to solving an equation with well, it's not an equation, an inequality. Let's just look at some of the ways to show them. So let's look at properties of inequalities. Just so you remember, we have three symbols. A is less than B. A is less than or equal to B. A is greater than B. A is greater than or equal to B. So just like we have an equation where P is some algebraic expression and Q is another algebraic expression, an equation states that they're equal. An inequality states that the quantity P in this case is greater than the quantity Q. In the methods, we're going to have the following properties of inequalities. This is called the addition property and the subtraction property. If A is less than B, then A plus C is less than B plus C. So let's get an example of that. We know that 3 is less than 20. So let's add some number to it. That says 3 plus, for example, 10 is less than 20 plus 10. And indeed, 13 is still less than 30. So we can add the same number to both sides of an inequality, and it doesn't matter which inequality symbol is being used. As long as we add the same number to both sides, then the inequality still remains true. So if the original inequality is true, then by adding the same quantity to both sides, the final inequality is still true. Here is the only different one. I mean, that really parallels the addition property. But let's unpack what these next two properties say. It says, well, suppose A is less than B and C is greater than 0. Then when I multiply both sides by C, then the inequality holds. So let's actually use that again. We have A is less than 20. So let's actually give you an actual number. We'll say 10 is less than 20. In other words, A is less than B. Let's let C be equal to 5. Well, 5 is greater than 0. So when I multiply both sides by 5, I get another true inequality. 50 is less than 100. Well, it's natural to ask the question, what happens if I chose minus 5 for C? Well, minus 5 is less than 0. Let's multiply both sides. 10 times minus 5 is less than 20 times minus 5. Well, this states that minus 50 is less than minus 100. But that's false. If we look at our number line, we're going to find if this is 0 up here, 0, this is minus 50, and this is minus 100 down here, and the direction of our inequality is this way. So minus 100 is actually less than minus 50, but this says just the opposite. So how do we fix it? We flip the sign. Maybe that's not a good color to use. We flip the direction of the sign, and when we flip the direction of the sign, all is well. To say that minus 50 is greater than minus 100 is the same thing as saying minus 100 is less than minus 50. So the rule here, which is expressed in number 3, is if I multiply an inequality by a negative number, to keep the trueness of the inequality, I have to change the sign. Notice this one's wrong. This is correct, this is true. But when I multiply both sides by minus 5, I have to change the direction of the original inequality, meaning just flip its direction to get the true statement at the end. So the only thing you have to remember is if you multiply or divide by an inequality by a negative number, you have to change the sign. But the cool thing is there's ways we can get around that. So a linear inequality is very much like a linear equation. In one variable, in this case our variable is x, has the form ax plus b is greater than 0. They can be written in that form. They can be written in many different forms, but this is the form that our book has given us. And in this case, a and b are real numbers, and a is not equal to 0. That's always the case. But when we solve inequalities, our solution sets are usually going to have an interval for numbers, tons of solutions, an infinite number of solutions. So we have to learn how to write sets as intervals. So let's just do a review of set notation. So this is a set. It's indicated by being enclosed in 2 curly braces. This is how you read it. X is always considered to be a real number. If it's not a real number, you'll either know it's not a real number, meaning it could be a complex number in context. In this case, we know it's a real number because, well, I told you, I don't know if you remember, is that for complex numbers, this part right here doesn't make any sense. To say a complex number is less than 20 doesn't make sense. So this is red. All real numbers x. This bar right here is read as such that those real numbers are less than 20. So let's see what that looks like on the number line. So I'll do my number line right here. It doesn't really matter. We do want to remember that it goes on forever to minus infinity to plus infinity. We're going to arbitrarily say 20 is right there, but the numbers in this set are numbers that are less than 20. 20 is not included. So to indicate that, we draw a circle with a hole in it. We say 20 is not included, and then one way to do it, and that's what I'm going to do right now, is just to scribble down here in red and say, okay, numbers x that are down here on this part of the number line to the left of 20 are what is included in this set. The easy way to express this set, however, that's a 1, 2, 3, 4, 5, 6. That's 7 things I have to write. Mathematicians instead use interval notation. So we're going to write going from left to right. We start with minus infinity, and minus infinity is not a number. So we always indicate what's called the open interval sign there. And I keep on going until I hit 20. But 20 is not included in the set either. So I indicate that by writing another open interval sign. So let's do another one. You should try to do this one on your own. So here, the set are, in English, all real numbers x such that those real numbers are greater than or equal to minus 10. So here's my number line. Again, goes on in both directions to infinity and minus infinity. And I'm going to arbitrarily say here is minus 10. It doesn't matter. You don't have to put a 0 in there. There's no scale. This is just kind of a visual schematic to help me know. And what numbers are in the set? Numbers x such that they are greater than or equal to 10. So in this case, 10 is actually included in the set. So I fill in that hole right there, and I indicate that the numbers in the set are the numbers greater than or equal to 10. So in interval notation, that means 10 is included. So when a number is included, I write what's called a closed interval sign, and that's on the left, and then I go all the way to infinity. You never can get there, so you indicate that by using an open bracket. That's called a closed, and this is called an open. This is a half closed, half open interval. So again, just to be clear, this is a set right here. This is a set. This is also a set. These two sets contain the exact same number. This interval notation is just another way of writing what's included in this set. So finally, we have all numbers x such that those numbers x are greater than or equal to minus 25 or less than 35. So again, we draw our number line, indicate that goes on forever, both directions. Here, if you want to put 0 right there, that's fine. Somewhere down here, you want to put minus 25, and somewhere up here, you want to put 35. It doesn't matter the scale. Again, this is just a schematic. So the numbers x are in between these 2 points, but x is greater than or equal to 25, so 25 is included, but x is less than 35, so 35 isn't, so it contains all numbers in this interval area right there, which we write this way. 25 is included, minus 25 is included, and 35 is not. So that would be the interval notation that contains the exact same elements as this. So an interval is a set. This is a set, so is an interval. This is just another way of writing this right here. So let's solve a linear inequality. So pretty much we're going to treat it almost exactly as if it were an equality. The only thing we have to worry about is if the coefficient to the variable term is negative, then if I'm going to divide through by a negative number, I have to remember to switch the direction of the inequality. But there's a little trick I'm going to show you that we can avoid that always. So this is example 1. So minus 3x plus 5 is greater than minus 7. So again, I want the variable term on one side. So what I'm going to do is subtract 5 from both sides. Or in other words, move 5 to the other side of the inequality. The price you pay as it changes its sign. So I have minus 3x is greater than minus 12. Now here I need to know how much x is. So you have two options here. You can divide both sides through by minus 3 and then change the inequality. But what I suggest is we don't really have to do that. Well, I mean, it's what I'm going to tell you to do results in the same thing. I'm going to use the addition principle to move my minus 3x over here. And the same principle to move my minus 12 over here. Now when I use the addition principle, I don't have to worry about changes in the direction of the sign. But notice when I do move my minus 12 over to here, I have to pay a price. And the price is its sign changes. When I move the minus 3 to the other side, 3x to the other side, it becomes positive 3x. And now the coefficient to my x term is positive, so I don't have to worry about flipping any signs. I just divide both sides by 3, so I get 4 is greater than x. So let's do it the other way. Minus 3x is greater than minus 12. So I'm not going to worry about it. I'm just going to go ahead and divide through by minus 3. That's fine. But in my next step, I have to remember to change the direction of the inequality. Minus 3x divided by minus 3 is x, and minus 12 divided by minus 3 is 4. Notice these two answers say the exact same thing. If I say x is less than 4, that's the same thing as saying 4 is greater than x. Well, we're not quite done because we want to express the inequality as an interval. So many of you don't have to draw the number line. The only reason I'm actually drawing it is because it helps you visualize a little bit better until you feel comfortable enough to do it on your own without drawing. So this is x is less than 4, or this says 4 is greater than x. X, 4 itself is not included. I always like my inequalities to point the small sharp end to point to the left. That's the natural direction of the number line. So now I'm just going to, this is where my x values live that make it true. You don't have to write x there, but I want to write it in interval format. So again, reading left to right, minus infinity is not included, and I get up to my 4, and my 4 is not included in either. So this is the answer in interval format to my original inequality. Minus 3x plus 5 is greater than minus 7. What it means is any x in this interval right here, or on the number line there, and there's an infinite number of them, if I plug an x in this interval, then that original inequality will be true. So let's go on to, I think we have another example of this. So just note that this inequality is less than or equal to. So when I say, let me talk about this, I always think, oh, this does not need any type of explanation. But then I encounter a student that's utterly confused by it. So when I say x is less than or equal to b, I'm really saying two things. I'm saying, I said x, but rather a is less than b. That's one statement. Or a is equal to b. If either one of these are true, then the original is true. So if I write 3 is less than or equal to 3, that's a true statement because 3 is equal to 3. If I write 3 is less than or equal to 107, that's a true statement because 3 is actually less than 107. So that's all I'm going to say about that, just in case. So this is example 2. So I have 4 minus 3x is less than or equal to 7 plus 2x. Now when you have variables on either side of your inequality, it's always, you're going to have to be moving them across the inequality side. You always choose to move the 1 over so that the resulting expression, inequality, will have a positive value of the coefficient of x. So I'm going to move it over. I'm going to do this in 2 steps. So the 2x stays together. When I move my minus 3 over, it becomes plus 3x. So I have 4 is less than or equal to 7 plus 5x. So my coefficient to my variable term is positive. But I have to isolate them. So that means I need to move my 7 over. And when I do so, it changes sign. So I have minus 3 is less than or equal to 5x. Notice that you don't have to worry about the minus being attached to the 3. You only have to worry about it when the coefficient to your x term is negative. But in this case, it isn't negative. So we can divide by 5 or multiply by 1/5. They're the same thing. And we get the answer. Minus 3/5 is less than or equal to x. So you should verify by on your own doing the number line that in interval notation this is the answer. So it's all numbers x greater than or equal to minus 3/5. So minus 3/5 is included in the set, and then anything going on up to positive infinity works. So here is an objective. We're going to solve an applied problem that uses inequalities. So these are kind of hard sometimes to set up the right inequality. So let's read through it. So if the revenue and cost of a certain product are given by, R stands for revenue, R is equal to 4 minus x, and the cost is equal to 2x plus 1,000, where x is the number of units produced and sold. At what production level does R at least equal C? So let's translate R at least equals to C. And then once we figure out that, we're going to be good to go. So what is R? There's a relationship of R, which is our revenue, and C, which is our cost. So we want our revenue, what we make, to be greater than the cost. So R has to be at least equal to C, but it's okay if it's greater than C. So R, our revenue, has to be greater than or equal to our cost. So this is our business model. But R is equal to 4x. And our cost is 2x plus 1,000. So now we're almost ready to go. At what production level does R at least equal C? And the production level is X. What is the number of units that we need to produce so that our revenue exceeds our cost? So literally, once it's set up, all we do is solve for X. So I have 4x, I move the 2x over, minus 2x is greater than or equal to 1,000. That gives me 2x is greater than or equal to 1,000. So I'm going to divide both sides by 2. So that gives me x is greater than or equal to 500. So if I sell 500 items or more, then my revenue is greater than or equal to my cost. So often, here are just some things to think about. When you're given applied problems, really, in some cases, it's not so easy to figure out the direction of the inequality between the two expressions. So one of the ways that I always do is just, okay, make your best guess. Solve the problem using the inequality sign called for the problem. You're not for sure about that. Well, just make a guess. And then look at your answer. Does your answer make sense using your given inequality? So suppose I had chosen instead R is less than or equal to C, then I would have to say that my number of units produced is less than or equal to 500. But then my revenue is never going to exceed my cost, because literally I could produce 0 products and I can't make any profit at all. So that wouldn't make sense at all. So as soon as you realize the conceptual error, you would just go back. In this case, you would just erase your inequality sign and flip it the other direction. So now let's solve a 3-part inequality. These are not near as hard as you might think. Indeed, you should remember these from intermediate algebra. So I'm going to tell you the meaning of this inequality sign. This is really a compound inequality. It's shorthand, but thankfully we can solve it really quickly. When I say minus 2 is less than 5 plus 3x, which is less than 20, what I really have is a compound inequality. Remember, a compound inequality is two linear inequalities connected by the word and is one choice and or is the other. When they're connected by the word and, you use set intersection. We're not going to have to worry about that. And when they use or, we have to use set union. So we will have to use and worry about unions eventually. So here, this is the same as minus 2 is less than 5 plus 3x, and 5 plus 3x is less than 20. So once I find out the interval that solves this inequality and the interval that solves this inequality, I take their intersection. And remember, the intersection of two sets, if that's set 1 and this is set 2, so here's set 1 and here's set 2, so anything within the boundaries of the first circle is in set 1, and anything in the boundaries of the second circle is in set 2. Their intersection is just whatever is in common to both. So this is their intersection. This is the picture of set intersection. If this is set A and this is set S, what's depicted here is the intersection of A with S. And that refers to that set right there. That upside down U symbol is intersection. Now on the other hand, if I have one set A and another set B, their union is everything in A and in B. So their union contains not only their intersection, but it contains things not all in their intersection, but in the set. So this is the set intersection. So if this is set, I'll call this set P, and this set Q. All of this area right here is the union of P and Q. I may have just said intersection. I meant to say union. So this is intersection. This is union. Intersection. Oh, I guess I need to use that. Intersection, this part in here, union, this part here. Anyway, as it turns out, you need to, that was just to review those concepts. We don't really need those concepts to solve this. These types of inequalities are really simple. We just treat it as if it were an equation, I mean a three-part inequality, not a three-part equation. So minus 2 is less than 5 plus 3x, which is less than 20. Here the rule is if I add something or multiply something, I have to do it to all three parts. So this is part 1, the middle part, and part 2. So again, we want to isolate our x term. So I'm going to subtract minus 5 to all three parts. And here I'm going to do it explicitly so you can see what's going on. So there I subtracted 5 from all three parts. So minus 2 minus 5 is minus 7. And that's less than 5 plus 3x minus 5. So that's just less than 3x. In other words, why did I subtract 5? I wanted to isolate the middle term so that there's x times a product of some number. And 20 minus 5 is 15. So now what do? I want to know what 1x is. Notice that the coefficient of x is 3. That's positive. If it were negative, I would have to multiply all three parts by a negative 1 and flip the signs. But thankfully it's not. So I'm going to divide the middle by 3, the right-hand side by 3, and the left-hand side by 3. 3 is positive. There is no sign flippage involved. So I get minus 7/3 is less than x is less than 15 divided by 3 is 5. And this is really easy to write as an interval just straight away. 7/3 is not included, but it's all numbers x greater than 7/3 but less than 5. So 5 is not included either. So that is the answer in interval format to my original inequality. Seriously? Okay, that's it. That's it for 1.7.